Thank you for introducing me. Hello everyone, my name is Wanju and I'm a PhD student at Seoul National University. Today I will introduce our work, PET Proactive Demotion for Efficient Tiered Memory Management. As we all know, memory usage has been exponentially increasing, while DRAM technology scaling has hit a wall. The graph on the right shows that memory accounts for more than 30% of the total data center power and cost. Under these circumstances, new memory technologies have emerged that generally offer higher capacity at a lower cost but higher access latency than DRAM. Therefore, a tiered memory system consisting of new memory devices along with traditional DRAMs is considered a promising approach for increasing main memory capacity at a lower cost. However, due to the high access latency of slow memory, the system could suffer from a performance drop if lots of accesses occur in slow memory. Therefore, in order to effectively utilize a tiered memory system, memory management that places frequently accessed data in fast memory and rarely accessed data in slow memory is essential. The management could be performed at various levels, but we focus on OS level management techniques, which offer application transparency without requiring hardware modification. Typically, OS level tiered memory management consists of three processes. First, they track access in various ways. Next, they identify the hotness or coldness of data. Finally, they demote cold data located in fast memory to slow memory, and promote hot data located in slow memory to fast memory. We classified existing works into two categories according to how they trigger demotion. Most of the existing tiered memory management schemes, including the Linux kernel, use a tight threshold to trigger demotion. When there is not enough free space in fast memory, they start to demote cold pages. They stop demoting pages if the number of free pages is greater than the threshold. For example, the Linux kernel defines 4 watermarks. When the free pages are less than the low watermark, the background kernel thread kswapd wakes up and starts to demote pages in the background. However, the default value of the low watermark is 0.1% of total pages, which means demotion is only triggered when free fast memory capacity is insufficient. On the other hand, several works have suggested proactively demoting cold data even when there are enough available pages in fast memory. They periodically track access to the fast memory and trigger demotion regardless of the fast memory usage. Proactive demotion have several advantages. According to the reports from Google and Meta, more than 30% of the data are not being accessed over 2 minutes. By proactively demoting these cold data, they can reduce the demand for fast memory, thus reducing the expensive memory costs. Or it allows more workloads to be executed within the same amount of fast memory. Moreover, proactive demotion can help mitigate severe performance degradation caused by fast memory shortages when there is a spike in demand for hot data. The graph on the right shows the ratio of promotion failure due to the deficiency of free fast memory of two non-proactive demotion schemes, autonomous tiering and auto-tiering, and one proactive demotion scheme, TPP. It clearly shows that non-proactive demotion schemes suffer from lots of promotion failure. The triangular markers indicate the amount of performance degradation. It shows that the high ratio of promotion failure ends up with high performance degradation. For example, in linear, autonomous tiering and auto-tiering fail most of the promotion and show a large slowdown of 69% and 88% respectively. On the other hand, TPP, which proactively demotes cold pages before reaching the critical memory threshold, results in only 5.8% performance degradation. Now let's talk about the reason why a new proactive demotion solution is needed. Proactive demotion essentially requires periodic access tracking to identify demotion candidate cold data. Since existing approaches on proactive demotion use the OS page as a unit of memory management, they either suffer from high monitoring overheads or adopt a proactive demotion approach that simply adjusts the watermark to initiate demotion earlier, thereby avoiding the need for periodic monitoring. However, the watermark-based approach fails to fully exploit the potential benefits of fast memory savings. To address these limitations, we focused on the memory access locality within a memory allocation unit. These figures show the memory access pattern of limlinear and XC from the spec benchmark. We extracted the virtual addresses accessed in main memory using PBS. The y-axis indicates the virtual address space for each benchmark, and the x-axis indicates the execution time. The yellow boxes represent the regions and lifetimes of memory objects which are allocated using malloc. We can easily see that the memory access pattern exhibits a high degree of spatial locality within individual memory objects. These results led us to extend the unit for distinguishing hot and cold data beyond the OS-managed page level to memory allocation units. To verify the possibility of using the memory object as a unit for proactive demotion at an OS level, we performed an experiment using optimized binaries obtained by manually modifying the source code of each benchmark. We first analyzed the source code to identify the code line where the memory objects are allocated and accessed. And then we modified the benchmarks to demote memory objects when each of them starts not to be accessed and promote them right before they start to be re-accessed. The graph on the right shows the fast memory saving and the slowdown of the modified benchmarks compared to the original binaries. The modified benchmarks save up to 84.7% of fast memory while incurring less than 3% of slowdown, demonstrating the feasibility of hot-cold data classification based on memory allocation units. Based on the previous experiment, we propose a new OS-level proactive demotion scheme named PET. PET uses PET block, P block for short, as a new tiered memory management unit, which reflects the unit in which applications allocate memory. PET consists of three mechanisms. First, the PET block capturing mechanism extracts a P block when an application dynamically allocates memory. Second, the demotion mechanism tracks the access in a P block granularity and performs proactive demotion through multiple steps based on P block information to reduce fast memory usage with low performance overhead. Finally, the promotion mechanism tracks access to demoted P blocks and performs promotion to mitigate the performance drop caused by slow memory accesses. First, I will explain our P block capturing mechanism. When an application dynamically allocates memory, the operating system compares the requested size with mmap threshold, which is 128 kilobyte by default. If the requested size is bigger than the threshold, the mmap system call is called and an mmapped area is created. Otherwise, the operating system expands the application's heap area using SBRK system call. Most operating systems divide a process's virtual address space into several contiguous, non-overlapping regions. In Linux, these regions are represented by VM area struct. Since these regions are created as applications or memory allocators request memory, they effectively represent the units in which memory is allocated. When a new region is created, the operating system merges the newly created region with adjacent existing regions. However, PET captures the unit of the generated VMA into an additional structure before merging. We named this additional structure as pblock. PET specifically focuses on anonymous mmapped areas, which are created for dynamic allocations larger than mmap threshold. As a result, PET allocates up to 217 P blocks in Graph 500 with 30 GB of working set, which is the highest number of P blocks per working set size among the benchmarks used. Also, it is noteworthy that there are over 7 million tracking elements when using a 4 KB page as a monitoring unit. Now let's talk about the demotion mechanism of PET. PET adopts sampling-based access tracking method in P block granularity. For each sampling interval, PET randomly samples one page per P block and clears the sample page's page table entry access bit. If access to the sample page occurs, the access bit is set. After a sampling interval is passed, PET checks whether the access bit was set during the previous sampling interval and samples another page. The scan interval is several times greater than the sampling interval. For each scanning interval, PET aggregates access information for each P block and determines if the P block is cold. We define the cold P block as the P block with no access detected during the scanning interval. Based on the access tracking information, PET categorizes each P block into one of 4 states for each scanning interval. If the P block is determined to be cold, it changes to the next state. And if it is determined that it isn't cold, it will change back to the normal state. When a P block is newly created or determined that it isn't cold in other states, the P block is initialized as the normal state. If the sampled pages have never been accessed during a scanning interval, the P block is considered cold and transitions to the phase 1 state. P blocks in phase 1 state are split into several temporary blocks, and access is tracked in each temporary block unit to improve access tracking accuracy. As shown in this figure, if the number of cold temporary blocks is greater than that of accessed temporary blocks, the P block is considered cold and transitions to phase 2. For a P block in the phase 2 state, PET randomly selects and demotes a portion of the temporary blocks named canary pages to further increase access tracking accuracy. We manipulated the protection bits of the canary pages so that the first access could immediately prompt a fake page fault. Same as phase 1 state, if the number of cold temporary blocks is greater than the number of accessed temporary blocks, the P block is considered cold. To take into account P blocks showing different access patterns within, PET splits the P block based on the coldness of the temporary blocks and only demotes the cold temporary blocks. Due to time constraints, I only covered PET's P block capturing mechanism and demotion mechanism in this presentation. For more in-depth information, please refer to the paper. Now let's jump into the evaluation section. We evaluated PET using the Intel Xeon processor with DRAM as a fast memory and the Intel DC persistent memory as a slow memory. We compared our work with various OS-level tiered memory management schemes. Fast only has sufficient fast memory, so it doesn't need any memory management. Base is the default Linux kernel which allocates newly created pages to the slow memory when the fast memory is insufficient. We added a promotion feature by enabling Autonuma memory tiering mode on Base and named Base Plus. We implemented Base Plus PD on top of Base Plus to evaluate the page granularity proactive demotion using a modern OS feature MGLRU. The red letters mean that it is classified as non-proactive demotion, and the blue letters mean that it performs proactive demotion. We also compared 4 previous works, 1 non-proactive demotion scheme and 3 proactive demotion schemes. We evaluate PET on several memory-intensive benchmarks. More detailed explanations of experimental setups and baselines are presented in the paper. We first evaluate the case when the aggregate residence set size is larger than the fast memory capacity. We tuned the benchmarks to have a residence set size of 1.5 times as much as the fast memory capacity and compared the execution time of tiered memory management schemes with that of the fast-only configuration. This graph shows the slowdown compared to the fast-only configuration, where lower values indicate better performance. PET shows the lowest slowdown of 5.7% on average, followed by TPP and Base Plus PD. We believe that PET, TPP, and Base Plus PD achieve relatively high performance because they rarely fail in the promotion and the fast memory allocation by triggering demotion proactively. However, thermostat suffers an average of a 14% slowdown due to its access tracking mechanism causing repetitive fake page faults. Although Daemon is also a proactive demotion scheme, it shows the lowest performance except for Base. We found that its access monitoring method, which scans the physical address space, makes memory management at the region level less effective for capturing logical locality. Next, we configured the benchmarks to have a smaller memory footprint than fast memory capacity and compared the runtime and fast memory usage of proactive demotion schemes with those of Base. Note that since the residence size is smaller than the fast memory capacity, Base uses only fast memory and runs in the shortest time. However, proactive demotion schemes proactively demote cold data regardless of the fast memory usage, which can result in performance degradation. This graph shows the slowdown of the proactive demotion schemes compared to base. The workloads marked with a red rectangle mostly consist of frequently accessed data. Therefore, if their data is mistakenly demoted, it can lead to significant performance degradation. PET exhibits the lowest performance degradation among the comparisons, even these hot workloads. This demonstrates that PET effectively prevents the slowdown by avoiding from proactive demotion when it is unnecessary. Consequently, PET shows the lowest slowdown of most of the benchmarks and achieves 1.7% slowdown on average. The bottom graph shows the fast memory saving ratio compared to base. PET saves 39.8% of the fast memory on average. These results suggest that adopting tiered memory systems with PET can reduce fast memory capacity requirements, leading to potential server cost saving while maintaining high performance. Or we can run additional workloads on the same system without compromising performance by using the saved fast memory capacity. To summarize this presentation, we classified existing OS-level tiered memory management schemes into non-proactive and proactive demotion approaches, and identified the potential of utilizing memory allocation units to enhance the efficiency of a proactive demotion. We proposed PET, a novel proactive demotion technique using a new management unit P block that approximates memory allocation units. Our prototype implementation of PET outperforms all baseline techniques, notably in scenarios where the application's resistance size is smaller than the fast memory capacity. PET was able to demote approximately 40% of pages with only a 1.7% average performance degradation. Thank you for your attention, and I'll be glad to answer any questions.